So good morning again, everyone. My name is Raed Karumi. I am a professor of bridge engineering in KTH, Royal Institute of Technology, and this course is about structural dynamics. So welcome to this first course and first lecture of structural dynamics. The lecture of today will deal with single degree freedom systems and the basics of structural dynamics. Okay, so the lecture of today will treat the fundamentals of structural dynamics and the single degree of freedom systems. Before starting the lecture, I want to show you some video clips from structures under vibration. We can start with the very well-known Tacoma Narrow Bridge. I think most of you have heard about this bridge and maybe also seen also seen some of these videos. So this is a bridge from the 40s that a suspension bridge that collapsed due to oscillations from wind-induced vibrations. Okay, so this is, as you saw, can be can lead to disasters of bridges falling down due to vibrations from wind. And this bridge actually collapsed after a month or two from suffering from high vibrations. These high amplitude vibration caused fatigue, and the cables were broke, and the bridge collapsed after that. Now there is a new bridge built, a suspension bridge, at the same location on the west coast in the US, and that bridge is much stiffer. They learned from lessons from this first bridge, and they made the bridge much stiffer to vibrations. Okay, but this is not only on bridges. I will share with you also another video clip from, let me see, also from, I will start the video. There you go. So you see here, I hope you can see it, a sign, a motorway sign that is vibrating due to also wind, high wind speeds. So, so these things like this can happen in bridges, in buildings, in sport arenas, in floors, due to something we call resonance. Okay, and that is something that we will discuss quite a lot in this course. Okay, so the aim of the lecture of today is to understand what is a dynamic problem, how can we make a model of the dynamic problem, how can we idealize a problem into what we call a single degree of freedom system. This is a system that can be described by one coordinate, one single degree. Also how to calculate the frequencies for such a single degree of freedom system, and also how to calculate the response, the displacements of a single degree of freedom system excited by a harmonic loading. So what is a dynamic problem, and what is the difference between a dynamic problem and a static problem? Well, this actually depends on the time for the loading. So if we have a load applied on a structure very, very slowly in time, then that is a static problem. That is not a dynamic problem. On the other hand, if the load is applied quickly on the structure, or the load is moving in position, for example, a vehicle moving on a bridge, then we will not have any more a static problem, we'll have a dynamic problem. Of course, then this depends on the time, what is the speed of this vehicle moving on the bridge. If it's moving at a crawling speed, then maybe we can still talk about a static or a quasi-static problem. If it's moving at a high speed on the bridge, then it's definitely a dynamic problem. So time-dependent loading will lead to dynamics. And the vibrations can be induced, as we saw on the Tacoma Narrow Bridge, by wind. It can be induced by traffic, for example, a train moving at 300 kilometers per hour on a bridge. It can be caused by humans, for example, on pedestrian bridges, human-induced vibrations on pedestrian bridges. This is, by the way, the subject of the PhD project of Daniel that will assist you. So Daniel is working on human-induced vibrations on pedestrian bridges, and Reza, the other assistant, he's working on traffic-induced vibrations on bridges. Vibrations can also be induced by machinery, for example, in industry, on the floor. Machines on the floor can induce vibrations. Can also be introduced by, for example, vibrating a ringing bell in a tower, like this, can induce vibrations. They can be introduced also by waves, for example, wave-induced vibrations on this turbine tower. This turbine tower, of course, suffer from wind-induced vibrations as well as wave-induced vibrations. But also the well-known problem of earthquakes. This is one of the most serious dynamic problems because it will lead to a lot of injuries and a lot of loss of buildings and bridges and infrastructures. And we will, in this course, learn how to design structures according to the Eurocode for seismic loading. Now, some of the vibrations can be also used for our benefit. I'm thinking, for example, of the concrete compactor that we use to compact concrete while casting. We can also think of the pneumatic hammer, which is used, for example, to break the concrete or any surface. So there are also vibrations that we can use in our daily life. Drive piling, for example, into the ground with a hammer to induce vibrations. So very good examples of useful vibrations. Vibrations can be characterized on the load types and the type of excitation. So we talk about a periodic loading, and periodic and harmonic loading. So first, periodic and aperiodic, we see that periodic loading is something that appears with a period, okay? This load doesn't appear at any period. There's no periodicity in this loading. So you don't know here where the next vibration will occur, so to say, in time. Here you know because there is the periodicity in the loading. Now, if the periodicity is also harmonic, like this, like a sine or a cosine, then we talk about a periodic and a harmonic load. Okay, so a periodic load, periodic but not harmonic, periodic and harmonic. Again, as you see here, periodic loading, harmonic periodic loading. A harmonic loading can be described with a sine or a cosine. And then we have an impact loading. This kind of loading has a very short duration in time. It can be a blast loading, for example. That's in time, probably only few milliseconds. Then there is random loading. This is a general kind of loading, which is random. For example, wind excitation can be a random loading, or a vehicle excitation can be a random loading if we have a lot of vehicles traveling on a bridge. You cannot, typical with random loading is that if you study any time instance here, you cannot predict what will happen in the next minute, okay? Because it's random in nature. If you have harmonic loading and you study here, and then you can predict what will happen here or here or here, because you know that the behavior of the load, it's harmonic. In this case, it's random. You cannot tell what will happen in the next time step. It's a random loading. Okay, some examples. Periodic loading, you have a machinery. Let's say it's a washing machine you have on the floor. That's a periodic loading. An engine from a boat, that's quite a periodic loading. A blast loading on a building, that's not a periodic loading. That's an impact loading, we call it. Earthquake, it's a typical random loading. So earthquake is a very good example of a random loading. You don't know what will happen in the next time step. The amplitude and the vibration levels and all of this is random. We can also characterize the vibrations in these types. We talk about free vibrations, we talk about force vibrations, transient vibrations, and steady state vibrations. So free vibrations, these are the vibrations the structure do when there's no external loading. So for example, we hit the floor, we jump on the floor, and then there's no loading on the floor. Then the floor vibrates in its free vibration. Or we hit a table and then we remove the load and then we have a free vibration. Force vibration is when you have the load acting with its dynamic on the structure all the time, and we talk about force vibration. For example, a washing machine on the floor, it's a force vibration. Transient vibration is the first time when you start, for example, a washing machine, the centrifuge of the washing machine, it will give you at the start high vibration levels, and then due to damping, these vibration levels will die out very quickly, and what you will end up with after a few seconds is a harmonic loading, which we call steady state vibrations. So transient is when the load is applied. The steady state is what remains after the transient have disappeared. So this is a good example of such a loading. You see in the blue line, this is the total response of the behavior, for example, of the floor where you have a washing machine. Okay, this is, let's say, the displacements, the vertical displacements of the floor. In blue, this is the total, which means the steady state and the transient. The first part is the transient here, the red dotted is the transient that will die out after 10-15 seconds. It will disappear. And as the washing machine is still in action, what you will remain in the vibrations is the steady state. And as you see in the steady state, the floor will vibrate with the frequency of the machine, okay? At a constant, nice harmonic motion, as you can see. Okay, so remember this, these are the 4 important types of vibrations. You have to understand the difference between them. Free vibrations, there is no load on the structure while the structure is vibrating. Force vibrations, when there is a load on the structure. Transient is when you apply the few 10-15 seconds when you apply the load on the structure. The steady state is the vibrations which remains after the transient have died out. Okay? Okay. So, single degree freedom systems. I think most of you have done the course on structural, on the finite element course in the spring this year. So you understand the concept of degrees of freedom. So degrees of freedom, these are the possible rotations or displacements of a structure, for example, the node of the structure. So, and the lecture here treats the single degree of freedom system, which means that a system which will consist of only one degree of freedom that can describe the motion. Okay, so if we look at this cantilever, which is fixed at this end and it's free at that end, this cantilever can be described, the motion of this cantilever can be described by this single degree of freedom system with only one coordinate, the u. The u is the vertical displacement, which is, for example, the vertical displacement at the tip of this cantilever. So the mass of the system can be idealized by this mass. Now this mass is not the complete mass of the cantilever, it's only part of it, because part of this cantilever is actually not moving. And as you can see here, the part here, which is at the fixed end, this is not moving at all. So that mass is not counted in this. So it depends on the boundary conditions and the mode shapes, how large is this mass. And then the stiffness of this cantilever is modeled with this spring K. Now, the spring stiffness K is Newton per meter, which is the force divided with the displacements, right? So it's force divided with displacements. That will give us the spring stiffness. If we look at our handbooks, we will find for a cantilever of this kind, we will find these equations for the displacements. I'm sorry that I have used the y instead of the u. Should say u here. So in the handbooks for the displacement of a cantilever, which is influenced by a force at the tip, cantilever with a length L and the stiffness EI, the displacement at the tip will be the force multiplied with the length to the power of 3 divided with 3 EI. Now, as I said, the spring stiffness is the force divided by the displacement. So if we take the force divided by the displacements, we'll end up with 3 EI divided by L3. This is actually the spring stiffness. Okay, so when we idealize this system, the cantilever, by a spring mass system like this, single degree of freedom system this, then we can replace the stiffness by 3 EI L to the power of 3. This is the stiffness of the spring. Okay. All what we do in structural dynamics is to evaluate the displacements and the accelerations in what we call time histories. So time histories is like diagrams that will have the time on the x-axis, and on the y-axis you will have the displacements or the accelerations. Okay, so these are called time histories. And to evaluate these time histories, we will use mathematical expressions that are called the equation of motion. And these equation of motions are expressed using what is well known as the Newton's second law of motion. So the Newton's second law of motion, what is this? Well, using that Newton's second law of motion, if we study a single degree of freedom system, now as you see, sometimes a single degree of freedom system will act in a vertical direction like this. Sometimes I will draw it in horizontal, but it's actually the same. So you have a mass connected to a spring, connected to some fixed point, and this mass is affected by a force, P. Now, as you see, P is changing with time t, okay? And this is a single degree of freedom system described with one coordinate u, and u is also dependent on time t. Now, if we pull this mass, a magnitude of u, okay? And then we can construct what we call a free body diagram. So this is the mass, and on the mass, we will put all the forces that are acting on the mass. So what forces do we have on the mass? Well, we have the external force, P of t, pulling to the right. We have the mass of the spring, the force in the spring pulling it back to the left. And the mass in this and the force in the spring, this is related to the spring stiffness and the displacements. So as we said before, the spring stiffness is the force divided by the displacement, which means that the force is the spring stiffness multiplied with the displacement. So this is the force in the spring. And then we have something else. We have what we call the inertial forces. Okay, the inertial forces. In Swedish, we call this tröghetskrafter. And these are related to the mass. Okay, these are the forces that you will feel when you are in an elevator and the elevator is accelerating or stopping. You will feel the inertial forces of your own body mass. Okay, and these are related to the acceleration. As you see, it's u double dot. So u double dot is the second derivative of the displacements. Okay, so the mass multiplied with the u double dot will give us the inertial forces. And if we put everything here in the equilibrium equation, we see that we have the pt on that side, we have the ku pulling on the other side, minus we have the inertial forces pulling to the other side, minus mu double dot t. And there are no other forces, so this is equal to 0. So this is the dynamic equilibrium equation for this single degree freedom system. Okay, before we take a break, let's have a look at this vibrating mass connected to a spring again. So we have a mass which is connected to a spring K, and by putting the mass on the spring will displace the magnitude delta. So this is delta is the static displacement due to the mass of the mass connected to the spring. Okay. So when we have connected the mass, the spring have displaced the magnitude delta. The mass, we have the gravity mg and we have the force in the spring pulling it up, which is K multiplied with the static displacement. Now, if we pull this mass a magnitude U downwards, okay, we pull it U and we release it. So it will go into free vibrations because we will pull it and then we will remove the load. By pulling it a magnitude X, then we will increase the force in the spring by the displacement X. Now X is changing with time here. So we can, I have here used the coordinate U instead of X. Otherwise, you can see here we have added the mass. It has elongated, the spring has elongated a delta. The force in the spring can be noted like this. This is the equilibrium, K delta mg. And we pull it a magnitude U. By pulling it a magnitude U, we can write the new equation, looking at the Newton's second law of motion. Again, we have the external, we have the gravity load of this mass m. We have the force, after pulling it a magnitude U, we have the force in the spring, K delta plus U. And we have the inertia force, which is reacting on the opposite direction, which is mu double dot. Now, as we have seen from the static equilibrium, the mg is equal to K delta, which means that this part and that part is equal to 0. What remains is Ku and mu double dot is equal to 0. And this is what we call the equation of motion. If we divide with m, we will end up with u double dot here, plus the square root of K divided by m, and the square root of K divided by m we call omega, which is the circular, we call it the circular frequency of the motion of this mass spring system. Okay, and this equation will describe the free vibration motion of this system. Okay. So I will stop recording now, and also, let me see, and we'll resume. Okay, so I have resumed recording. I forgot to start recording after the break. Anyway, so let's have a look at this example. So in this example, we have a concrete slab resting on 2 springs or 2 piles. Okay, so the mass is given 750 kilograms per meter. The stiffness of each spring is 3 meganewton per meter, and we are asked to calculate the frequency. All right, so the frequency is square root of K by m. Okay, so the frequency is square root of K by m. And as you see here, the circular frequency, we have 2 springs. This is the spring coefficient. We have 2 springs. And as you see, 10 to the power of 6, because this was given as 3 meganewton per meter. So now we have it in Newton per meter. And the mass was 750 kilogram per meter, and it's 2 meters. So 2 meters, 750. This is the mass of the slab. So this is the circular frequency, and if we divide with 2 pi, we will get it in the frequency as 10.1 hertz. Okay, so this means that if we will pull or push this mass, and then we will remove our hand from this mass, it will start to vibrate 10 times per second. So it will go up and down, bounce up and down 10 times per second. Okay. If this is good or bad, we don't really know, because it depends on the force acting on it. So 10 hertz can be good, it can be bad. depends on what kind of force we have on this slab. Okay. So now we had, now we had two springs. Now we had two springs, and as we've seen, we added, oops, sorry. Now we had two springs, and as you saw, then we added, or we multiplied with 2 to get the total spring, because they were in parallel like this. If the springs are not in parallel, if they are in series like that, okay, then actually this expression will apply. So you take K1 inverse, K2 inverse, add them together, and that is equal to 1 by the total K. Okay, so if you can have several K1, K2, K3, K4 in series, you can calculate the total K corresponding to that using this expression. And how do we get this expression? Well, by studying this mass, we pull it a magnitude of 1, and then we will have U1 displacement here, F1 force, U2, F2 force, and then we have K1, K2, and the total force we are pulling it with is K, because it's a displacement 1, so the force will be K multiplied with 1. Okay, so the forces F1 will be the spring stiffness in 1 multiplied with the displacement in 1. The same thing, the force in 2 will be the spring stiffness in 2 multiplied with the displacement in 2. But of course, the forces have to be equal due to equilibrium. The force acting on the mass must be equal to the force F1 and F2. And then the displacements of spring 1 and spring 2, in total, it should be 1. So in this equation, if we replace the U1 and U2 with F1 divided by K1, this would be F2 divided by K2, we can then simplify this into this equation, okay? It happens in the exam sometimes that I give you a system with consisting of a mass and maybe 2 springs in series and 1 spring in parallel, and I ask you to derive the total spring stiffness, okay? So this is how you do it. On Canvas, I have uploaded this table that give you some expressions for the spring stiffness for different cases. As you see here, for example, this is for a single spring. The stiffness can be calculated as EA by L if we know the kind of material and the area of the spring, and the length we can calculate L. I will show you how to do this. And if it's 2 spring in series, if it's in parallel, we just add them. For the cantilever, as you saw before, we can look in our engineering tables. Now, how do we get this? Well, this is simply by looking at Hooke's law, which is epsilon multiplied with the E modulus equals sigma. Now, epsilon can be replaced. Epsilon is delta L by L, so the elongation divided with the initial length. The elongation is U, and the initial length is L, the E modulus, and then the sigma is the force acting divided with the area. And now if we take the force divided with U, this will give us the spring stiffness, the spring coefficient here. And then this will be EA divided by L. Okay, so this is how we get K equal EA divided by L just by using Hooke's law. Now this applies, for example, if you have a pile. Okay, if you have, let's say that you have 10 piles and under a concrete slab, and you want to replace the 10 piles with 1 spring, okay? They are in parallel, then you can just add their stiffnesses together. And you have, so the A will be the area of each pile. E will be the E modulus of each pile, if it's in concrete or steel. and L will be the length of each pile. And then you can add them together into one total stiffness for the pile foundation. Okay. So let's see how we can solve the equation of motion. I will not go through the general solution of the equation of motion. You will find this in the textbook of Chopra. You will find this actually in any textbook on structural dynamics. And it will take like half a lecture to go through the derivation of the solution, but I will show you the principles and the main equations. So now we have again our mass system. We have also added a spring. And as you see here in the dynamic equilibrium, what have been added is this extra term for the spring, for the dashpot force, because the dashpot is a hydraulic dashpot, which is develop a force in relation to the velocity. Okay, it's a viscous damper. So a viscous damper will develop a force in relation to the velocity of motion. And the velocity of motion is denoted with u dot. This is the acceleration, this is the velocity, and this is the displacement. Okay, so we had just added, when we look at the free body diagram, we have the inertial force, we have the spring force, and now we also have the damper force. If we divide with m, we will get this equation. And as you see here, there is nothing on the right-hand side, so there are no external force. That's why we talk about the free vibration. And we want to develop the solution for the free vibration of this system. So free vibration, there is no force. We know that the free vibration of such a system is always harmonic. So the free vibration can be described with a sine, cosine, or exponential. So this exponential function can be also written as a sine and a cosine. Okay. So in some textbooks, they choose to write it in an exponential function because it's simpler for the derivation, but you can as well use sine and cosine. So we can describe this as this is the main amplitude of the vibration, u, and then this is the harmonic part. Okay, t is the time, s is a parameter. Now, if we differentiate this to get the u dot and the u double dot, what we will get? So this is the original. We differentiate once for time. So u dot. What will happen? This function will repeat itself. So the s will come in front here, right? So this will be again the same as the original, but we have added s in the beginning. Okay. If we differentiate again with time, again, this will repeat itself, but the s will come here again. So we'll have s to the power of 2. Okay, so this is the u dot and the u double dot. If we put these in this equation, we can simplify this into that one. Okay, so you see this is common for all the terms. So we can have it outside here, and inside the brackets, we'll have this function. And of course, this cannot be 0, so this sum must be 0. And then this characteristic equation can be solved to give us the parameter s. So in this equation, everything is known. The mass is known, the damper is known, the spring is known. The only thing which is unknown is the s. And of course, then if we have the s, if we solve this and we get the s, we can get the u, and how the u depends on time. Okay, so this is the solution of that characteristic equation. Okay, so this is the characteristic equation, and this is the solution of the characteristic equation. Now we can define a few things. So you have seen the definition of the omega n, the circular frequency, which is square root of k by m. We can define a new parameter called beta, which is the ratio between the s and the omega n. And then we can define a parameter called the critical damping, which is the parameter that will give this 0. Everything under the square root will be 0 if the critical damping is this, if C is equal to that. Okay. If C is equal to this, then all this will be 0. So we call this critical damping. And then we can define another parameter, super important parameter, which is called the damping ratio, Xi. Xi, the damping ratio. This is the damper coefficient, C, divided with the critical damping. Okay, this is the critical damping, and this is the damping in the system. So by defining the omega, the beta, the critical damping, and the Xi, we can enter this in the equation, and we can then also write the solution UEST, into UE. Instead of S, we have the beta omega n and the T. Okay, and the solution for this, you can go through the derivation of this in the textbook. The solution will be depending on the beta. Okay, so the beta, as you see here, again, from here, the beta, this is just a way of rewriting this equation here. Okay, so we have rewritten this equation, considering the beta and the Xi into this equation. Okay, and this equation has 4 solutions, 4 possible solutions. Fortunately, we are only interested on the 2 simplest ones. The first solution is when we have 0 damping. So if we have 0 damping, so C is 0, then Xi is 0. If Xi is 0, then this will be 1, this will be 0, and the beta will be plus minus I. I is the imaginary number, okay? So beta will be plus minus I. And then we can put beta plus minus I in here, and we will get this solution for the differential equation. And this is the undamped system. So undamped because we have Xi equals 0. Xi equals 0 will give us the beta equal plus minus I, which will give us the solution U equal to this. And this can be described as an exponential function, or as a sine with a cosine, or with a sine and some shift, okay? And this is actually a very important case. If we try to plot this motion, so we see here the time history and also the response of the system in the circular diagram. We see the displacement in red. So it starts here and it has some periodicity with t equal to 2 pi divided with the circular frequency. And then the displacement is red, the velocity is blue. Interestingly, you see that when the displacement is 0, we have the maximum velocity, okay? And this is not so strange. Imagine that you have this mass connected to a spring. When the mass is in its 0 position, then you have the maximum velocity when it's moving, okay? But when the mass has its maximum, position, then it stops and it returns back. Then the velocity is 0 and the acceleration is high, okay? So as you see, they are always, when the mass is in its turning position, the velocity is 0, but the acceleration is high. And when the mass is in 0 position, the acceleration is 0, but the velocity is high. So again, you can describe this here, or you can describe it in a circular way also. And the amplitude, another thing which is interesting that you have to remember is that the amplitude is always, as you see here, this is if C is the amplitude of the displacement, the amplitude of the velocity will be C multiplied with omega, because it's, if you differentiate this once, okay, it will be, so U dot will be C multiplied with omega multiplied with the cosine of this. If you differentiate it again, U double dot will be then C multiplied with omega twice multiplied with the sine again. So the acceleration will have a higher amplitude. The velocity will have also a little bit higher amplitude than the displacement itself. Okay, so that was the first case. The second case is if C is not 0, we have some damping in the system, but it is very low. So we call this under-damped system. So Xi is less than 1. If Xi is less than 1, the beta, this is the expression we got for the beta, Xi is less than 1, so this will be positive, and this will be a negative number here. So we put this in the equation and we can solve for this. What we will obtain is a response which will look like this. We will have some oscillation, but the oscillation will die out after a while due to the damping. If we have low damping, this will take longer time. If we have high damping, this will take a shorter time. Okay, so this will be described as before with this sign, but now we have added this exponential function, which is the damping in action in this vibration. Okay. And then the case number 3 is when C is equal 1, which means that the damping is the critical damping in the system. The beta will be 1, and U will be described like this. These cases are actually uninteresting for us because they are more for mechanical systems, like when you are designing satellites and airplane wings and things like that. And you have an overdamped system. In the overdamped system, then Xi is even higher than the critical damping, higher than 1. This will result in no vibration. As you see, the response will be non-vibrant response. Okay, so in certain cases, depending on the device that you are designing, if it's an X-ray machine that are not allowed to vibrate, or a satellite antenna that are not allowed to vibrate, then you might design it for overdamped or critical damped systems. Otherwise, in all our civil engineer structures, we have undamped or very low damped structures. I will continue with example 2. I see there are no questions in the chat yet. Okay. So example 2. This is the exact same foundation we had before. You remember in the last time we looked at this example, we studied the bouncing, the vertical vibrations. But of course, this system, it can also rotate, okay? Depending on where you place the force. If you place let's say that you have a washing machine on this, if you place it in the middle, of course, then it will give you probably only vertical vibrations, mostly. If you place it eccentrically, it will also give you a rotational motion, okay? So a system like that, which is resting at 2 supports with some distance, it can rotate and it can translate. Okay, so it's the same data. we have 750 kilograms per meter. We have a spring stiffness. Each one of these is 3 meganewton per meter. And we are asked to derive the equation of dynamic equilibrium for the rotation and determine the natural frequency. So now we will consider rotation. Imagine that this can rotate like this. Then when it rotates, we can write the expression for the sine of the angle of rotation. Phi is equal to this displacement divided with the distance to the rotation point. Okay. The rotation can be considered very small in this case, so we can assume that small rotations, which means that the sine of the angle can be replaced by the angle itself. So sine phi is equal to phi. Then we can write the displacements at the tip here as phi multiplied with L. And then we can put the moment equilibrium of equation around the center of gravity, around this point. So we will have the moment mz around point z. And then we will have the moment that comes from these two forces. So we have two forces. The forces are related to the spring stiffness and to displacement. The displacement is V. Spring stiffness is K, so the force is K multiplied with V. Then we have two springs, and then the distance is L, so this will give us a moment. This moment is going on the opposite direction to the moment mz. Now we can see the moment mz as the inertial rotation. You remember that when we had translations, we had inertial forces. These are the forces that have an opposite direction to the motion, to the translation. We can have a similar thing in rotation. We can have a moment which counteract the rotation, okay? And this can be described by if you remember from mechanics, I don't know which year, if it's the first year in the program or the second year you did a course on mechanics, but I'm sure that you have seen this in mechanics, that we talk about the J, which is the mass moments of inertia. Okay, so so the J multiplied with the angular acceleration. So the acceleration phi double dot, the acceleration of rotation, multiplied with the mass moment of inertia. This will give us a moment that counteracts the motion, okay, and an inertial moment. And then we have the forces from the spring that produce a moment. And then if we divide with the J, we will get this equation, exactly as we did for the translation. For the translation, we had M, which was the mass, multiplied with U double dot. The M multiplied with the M multiplied with the U double dot gave us an inertial force. Here we will have an inertial rotation moment that will come from the rotation. Okay, so instead of the mass, we will have the J, which is the mass moments of inertia. And instead of the displacement, U double dot acceleration, we will have the angular acceleration, phi double dot. And then if we divide with J, we'll get this equation. Okay, so we can compare this equation with the one we had for the translation. So this is the previous one we had for the translation, and this is the equation of motion for rotation. Okay, If you remember when we had the equation of motion for the translation, we said that the omega square is this. So omega is equal to the square root of k by m. So we can, in the same way, say that the omega here is actually equal to the square root of this in a similar way. So we can solve this equation, differential equation, in a similar way, and we'll get the omega is equal to the square root of 2kl squared by j. From your handbooks in mechanics, you can see that you can find the mass moment of inertia. So for a point mass, the mass moment of inertia is the mass times the square of the perpendicular distance to the rotation point. So it is this distance from here to the point where we want to calculate the displacement or the frequency of the system. We can calculate it like this. Also, the mass of the system is 2 meters multiplied with 750 kilogram per meter. This distance is 1 meter. It's this one. It's from here. So in total, it's 2 meters. So from here to there, it's 1 meter. And divided by 3. So this is the mass moment of inertia. And then to calculate the frequency, it's a square root of this. So 2k, this is the k. We have 2 springs. This is the distance from the spring to the center of gravity. So the spring is here. Distance between the center of gravity and the spring is 0.8 meter. This is here. And then we can calculate, and then we get 14 hertz. So in example 1, we solved this for the translation. And in example 2, we solved this for the rotation. And we found here that for the vertical motion, we have a frequency of about 10 hertz. For the rotation, we have a frequency of 14 hertz. And the way this moves, we call it as a mode shape. So this is mode shape number 1. This is mode shape number 2. So this is the shape of the motion, mode shape. Again, these numbers do not really tell us at the moment anything, because in order to know if these numbers are good or not, we have to have an idea of the force acting on the system. So if we have a force acting in the middle with, say, 10 hertz, or a force acting eccentrically with 14 hertz, then we can get problems. Okay, so in order to know, we have to study the force acting on the system. I will stop here, and let's have time for questions.